Hello friends, welcome to my channel. Let's have a look at problem 337, House Robber 3. This video is a continuation on house robber problems 198 and 213. So this house robber 3 involves binary tree because the thief improved in data structure and algorithms. So a binary tree actually can be defined recursively. So here we could think of giving a recursion solution. So the thought process is still following the previous two problems. However, the code format is slightly different due to the different abstract data types. So here is a binary tree, and in previous the data structure data type is list. So first I'll read through the statement of the problem, and then we analyze the problem, and finally we share the code. So here the thief has found himself a new place for his thievery again. So there is only one entrance to this area called the root. So that this root is the root of the binary tree. So besides the root, each house has one and only one parent node or parent house. So after a tour, the smart thief realized that all houses in this place form a binary tree. It will automatically contact the police if two directly linked houses were broken into on the same night. So given the root of the binary tree, so return the maximum amount of money the thief can rob without alerting the police. So here are two examples. So let's look at example 1. So in example 1, so if the thief robs the root and the two leaf nodes, so he can or she can maximize the money collected, that is 7. And in example 2, so the two nodes marked in red are the nodes to be robbed to maximize the money, so that is none. So we're going to analyze this further. So before we look at the methods, let's look at the constraints. First, the number of nodes in the tree is in the range between 1 and 10 to the power 4. So this first says that the tree as a whole is not null, and 10 to the power 4 is the upper bound of the number of nodes. So this first constraint actually defines the problem size. And secondly, so the node value is not negative. So this is actually can be important because each node couldn't have negative money. So with that said, let's look at the idea. So here for each node, so actually we're going to compute two pieces of information. So not rob or rob. So the rob means the maximum money can be collected onwards if we rob or the thief robs that node. The not rob can be interpreted similarly, but if we do not rob, but the condition is that the thief does not rob that node. So with these two pieces of information defined for a node, so the main point for this problem is how to get the information for a root if we know the information for its two subtrees. So this is a counterpart of the recursion relation in the previous DP solutions to problem 198 and 213. So there we speak of DP update rule or recursion relations. So here is similar, right? So given a root or node, so we assume that for the left subtree, so if we do not rob the left subtree, so the amount of money we can get is left not rob. So if we rob the left subtree node, so we get left rob. So this is the amount of money if we rob the left subtree root. So similarly, we define the two pieces of information for the right subtree. So then we could get the information for the root. So if we do not rob the root, then we can rob the left subtree or not. Similarly, we can rob the right subtree root or not. So in this way, so the maximum money we can get is that, so this is the first item. The first item means that we can choose the van larger, depends on if we rob the left subtree root. Similarly for the right, so the maximum is that the maximum money can be collected depending on not rob the right subtree root or rob, right? So this is if we do not rob the root. So if we rob the root, then we cannot rob the left subtree root and the right subtree root. So then the money can be collected as root value. So this is the money at the root node. And then we plus left not rob. In other words, so we cannot rob left root anymore. So similarly, we add right not rob. In other words, we cannot rob the right root anymore, right? So this is the update rule of the recursion relation in a not so rigorous sense. So here, let's look at example 1. So for this node 2, so the information is the following. So if we do not rob this 2, so we can get the money 3. And if we rob this 2, we can get money 2 because we cannot rob 3 anymore. So for the 3, for this the right subtree of root 3, so if we do not rob this 3, so we can get 1 unit of money. And we rob 3, so we can get 3 units of money. So the information for 2 and 3 is 3 2 and 1 3 respectively. Then for the root tree, for the root 3 here, so if we do not rob the 3 itself, then the money we can get is the max of this one plus the max of this one, that is 3 plus 3, that is 6. So if we rob 3 itself, then we should have 3, this is the value at the root, and then plus not robbing 2, so we get 3 here, and not robbing the right subtree, that is 3, so we get 1. So we get 3 plus 3 plus 1, that is 7. So overall, the largest one is 7, so the return is 7, because 6 and 7, the larger one is 7. So the plan in this video is the following. First, we are going to share a pure recursion solution, and then we will write a DP-like solution in line with the DP solutions for the previous 2 problems. So the 2 formats are actually essentially the same. So now, with that said, so let's look at the code. So first, I'm going to define a hyperfunction. So this hyperfunction actually essentially does the actual work. So this function accepts a tree node. Let's call it root, or you can call it a node. So that does not matter. So then first we're going to have a stop condition or base case if not root. So in this case, if the node is null, so we're going to return 0 0, right? So no matter we rob this root node or not, there's no root tree node at all, so we get return 0 and 0. Otherwise, so we do recursion calls. So first L is helper root left, and R is helper root right, right? So notice that L and R are 2 tuples, right? And then we want to combine the information from L and R according to the rules here, right? So first we're going to return. So if we do not rob the root, so we can rob left subtree root or not, or similarly for the right tree. So we're going to have max L plus max R. So this is the first item in the return tuple. And then if we decide to rob the root, so we are going to have root value, then plus the situation that we do not rob the left subtree root and right subtree root, that is L0 plus R0. So that's the hyperfunction. And now with this bulk of work done, so actually we are ready to return. So we are going to call this hyperfunction, right? and apply it to the root, and then this is a tuple. Then so this actually contains two pieces of information. So the money we can collect it if we do not rob the root, and if we rob the root, then what we are going to return is the max of the two, right? So in other words, the max of the two elements in the tuple. So that's actually finished the first format of solution. So I will change this one to be solution. And then we are ready to do a special case check first. Yeah, it passes the example 1 here, I guess. So now let's do a generic case check. Yeah, it passes the generic cases. So with that said, actually, we are ready to do the second version. So here, let me copy this function signature and put it here. And then we'll change this function name to be robv1. So now let's look at the second one. So in the second one, what we are going to do is that we write a dynamic programming solution, or dynamic programming lag solution. So the purpose for this format of solution is to align with the two videos for house robber 1, house robber 2, right? So that we can see that we can use dynamic programming to address all the three questions. So with that said, we are ready to do the work. So for this solution format, I'm going to use memorization, or we can use cache. So I'm going to initialize dictionary called memo. So now we're going to define the robber, so or the worker. So let's see, I'll define it as robber. And then this we're going to accept a node and a state. So let me make some remark. So node will be the tree node, right? Or the binary tree, and the state will be a boolean. In other words, if we rob this node or not, right? So the return will be the money, right? So the money we can get onwards from the tree node, right here. So this function actually can be easily written. So right. So first, let's consider a case if node and state not in some dictionary. So we need to do some work. So otherwise, we just need to return memorization and the node and state, right? So this is the structure of this hyperfunction. Now let's look at the main logic. If node and state is not a key in the dictionary, then what we're going to do? Let's check if not node. So we're going to return 0. So this is for sure, no matter what's the state, true or false. And then we are going to check if the node is not null, if state. In other words, if we decide to rob this node. So what we're going to do is that we update this dictionary, right? So we have the node and state. So it's going to be because we have decided to rob this node itself. First, we need to include the node value here. So node value, right? So this is the one part. Another part is that we can rob the left and right, right? So we can rob. So because we are going to rob this node, we cannot rob the node left and the node right roots. So we're going to rob node left. So the state variable will be false. And then we're going to rob node right, but we cannot rob the root. So it's also going to be false. So this is the first case. Otherwise, if the state is false, in other words, we will not rob this node. So what we are going to do is we will still update this dictionary. But here, so because we have decided not rob the node itself, then we can choose the maximum value we can get from rob node left and node right, with the option that we can rob the corresponding root nodes if we like. So that is max. So rob node right. So let's see, false, or rob node right true. So similarly, we need to add the left subtree. So rob node left false, and rob node right true. Right. So this is the maximal amount of money we can collect. So that's actually the full logic for this case. So that's done. So we just need to return the result here. So that's the full hyperfunction. So now what's the return for the whole problem? First, we're going to call this function, right? So call this function, there are two possibilities. We either determine to rob the tree root and or not, right? So if we rob the tree node, so we're going to have root and true. Otherwise, we're going to have rob root and false. So we're going to collect the larger one. So that is the maximal of these two. So that's the second format of solution. So here we use memorization, and this is a format of DP solution. So with that said, so this is also in a recursion format for sure. So we are ready to do a special case check first. Let's run the code. So run answer. So let's see what's the problem here. So if node state not in, so we're going to if state. So node value left and right. So yes, and memo node state. So max rob node right false, right true. So here should be left. All right. So we collect this spelling typo. So now let's do a check again. Yeah, it passes the test case. So now let's look at the generic case. Yeah, it passes all the test cases. So I guess that's about it for this problem itself. So let's give a quick summary. So in this robbery problem, so the problem involves binary search tree. So first, we follow the previous ideas in solving the two house robbery problem 1, 2, and then we use dynamic programming, and also we use a recursion format. So in the specific implementation, we first demonstrate a recursion solution, and then in order to align with the previous two videos, we write a DP-like solution, right? So with that done, I guess that's about it for this video. Thank you very much.